Hello, everyone. We will get started on our talk here in just a few moments. We will give everyone a little bit more time to join. This is going to be the second in our Heterogeneous Compute series, so please hang tight and we'll be right back with you. Hello, everyone, and welcome to the second in the Gen Z Consortium Heterogeneous Compute series. Today, we are going to be talking about the evolution of heterogeneous compute using Gen Z Fabric. And our presentation will be provided by Hiren, Patel, and Erich Hanke from Intelliprop, Inc. We will have questions at the end of the call, so if you do have a question, please use the question mark symbol in the right side of your screen to submit those. And with that, Hiren, please take it away.
All right. Well, thank you, Rachel. Erich and I are glad to be here to discuss the evolution of heterogeneous computing using Gen Z. The agenda for the webinar today, Erich and I will go over what is heterogeneous computing, why it's interesting, and what challenges there are. Then we'd like to go over some of the guiding principles for heterogeneous computing using Gen Z fabrics. I'd like to take a step back and go over what we've done and what we've learned. After that, we'll go over some new things, some cool things that we're going over or where we're going. And then at the end, Erich and I would be happy to take questions. So Erich, let's start. What is heterogeneous computing?
Thanks, Hiren. So yeah, let's get started. So companies who have been working on making CPU for the last 3+ decades have made amazing exponential improvements in computing power over that time. While some claim Moore's law is not dead, the exponential growth has certainly started to drop in more recent years. There are many reasons for that. I'm not going to dive into them here, but the main takeaway is that there's a specific need for new ways to accelerate processing efficiency in ways beyond just cranking up core frequencies and adding additional cores. Heterogeneous computing is unanswered to that particular slowdown in general purpose computing improvement rate. It's a system architecture approach that allows mixing of different processing elements running different instruction set architectures to collaborate in order to solve a specific problem. Additionally, accelerators such as GPGPU, data processing units, FPGA, and ASICs have been added into the mixture to further improve system efficiency in processing data. At the end of the day, it's all about the data and how fast and efficiently that data can be acted upon. So all of this is great, and we'll spend some time diving into the details as we work through this deck. But fundamentally, Gen Z Fabric allows for scalable solutions, enabling complete peer-to-peer traffic in an environment which supports hardware-enforced isolation and flexible security built into the switches and components and managed by a flexible fabric management software entity. So we touched on this a bit in the previous slide, but general purpose CPU are fantastic for their simplicity in programming and rich availability of software support. But they started to lose their steam a bit for certain high performance applications. Designing purpose-built accelerators which perform very specific operations can complement these CPU for improvement in total system performance. Goes without saying, but DRAM and accelerators are expensive. We want to be able to share these resources dynamically as application demands spike in order to improve total cost of a particular system solution. So infrastructure is maxed out. CPU cores in a server processor have been increasing year over year for a while now, which is great for virtualization. But I/O bandwidth and memory bandwidth per core are both down over that time. A heterogeneous compute environment, which has been configured in the right way, can help improve this by spreading memory controllers into the fabric and offloading from CPU. There have been other approaches to improve memory bandwidth, such as the inclusion of high bandwidth memory, but these are expensive solutions and fairly limited in the total capacity supported. So how Gen Z can help? Gen Z allows composability of resources in a scalable manner, enabling medium to very large networks of components, which can be a mixture of compute, accelerators, memory, switches, SmartNICs, or storage. Using Gen Z, networks can be configured with multipathing enabled, allowing those expensive resources to be accessible even if a node goes down for maintenance, improving uptime and availability. The ability to deploy, retire, and redeploy resources allows for efficient use of those resources and eliminates the need to build for worst case on day one. Resources can be purchased independently and added to the fabric as dataset grows or application demands change. And something that's been happening for a while now in the storage market is media can change and evolve independently from CPU and accelerators. Keeping the Gen Z fabric the same, solution providers can make changes to their media independently from CPU release cadences, so these technologies can evolve and be deployed independently. So that all sounds wonderful, but there's no free lunch. Heterogeneous compute is not without its challenges, and here are a few of them. How to design data structures and algorithms that take advantage of disaggregated architectures. This is similar to the problems our industry faced some time ago when transitioning from single-core CPUs to multi-core and the challenges which needed to be solved for multi-threaded applications. The legacy software can and must still work, but there's opportunity to look at things a little bit differently and take advantage of this heterogeneous computing environment. Accelerators are inherently more complex to program than traditional programs running on CPU out of memory. This is there's been some recent efforts around improving the programmability of GPU, for example. They're still a bit cumbersome. There's been good progress, but still some ways to go. Not all of the changes are bad, however. So what would you do if you, or what could you do if you had a system that could malloc 100 terabytes of memory? This unlocks new potential. Along with that potential, there's new challenges. But that sounds like a pretty interesting challenge to me. There's also interoperability issues that need to be worked through when dealing with multiple ISAs running on different compute engines, such as CPUs or accelerators. All of these different component types also need a management scheme that understands how to configure and deploy in a controlled, isolated, and secured way. So here are three simple guiding principles for heterogeneous compute being deployed on Gen Z fabric. Number one, don't break legacy software. If your software wants to use memory that's malleable and cacheable to the CPU, you better ensure that it can run even with fabric-attached memory. Effort should be made to communicate the numinous of that memory, latency and persistence characteristics, for example, but it should still run the application. As Hiren will talk about in a few slides, one of the first Gen Z POC bridges presented an NVMe endpoint to host software, and each of the Gen Z memory modules were presented as a separate NVMe namespace, all using completely unmodified operating systems and NVMe drivers. This was great because all the block device software that already exists need not know anything about Gen Z, and it just worked out of the box. Those apps and utilities had no knowledge of Gen Z whatsoever. The side benefit was pretty high performance, which was enabled, and some pretty interesting use cases for that proof of concept. Principle number 2 is make improvement to the libraries where possible. If there's specific functionalities that run more efficiently using some accelerator or perhaps Gen Z atomics, effort should be made to stuff those changes down into library calls. Make those Gen Z aware changes in the OpenFAM or libfabrics libraries, for example, and keep that hidden as much as possible from the application. Application writers may eventually want to make changes to apps to take advantage of some of these new whiz-bang features, but they'll certainly be unhappy if their app breaks from the start. Principle number 3, try to minimize unnecessary data movement across the fabric. So this is an interesting one to keep in line with principle number 1. So we need to be able to support loads and stores coming across the fabric to and from that fabric-attached memory. We get improvement here when using a low latency cacheable host connection like AXI, for example, when using an ARM processor, or host buses like UPI or CXL. That FAM is still cacheable to the host cores. As such, the loads and stores typically will be full cache line adds and evics and efficiently make use of host CPU caching architectures. But with accelerators or computational fabric-attached memory devices, you can move some of that processing to the media controllers or accelerators themselves. This can offload some of the host CPU cores and distribute the work to run closer to the actual media, minimizing operational latency and energy on a particular operation. Additionally, since Gen Z is a fabric, it can support non-tree topologies, very flexible topology schemes, and peer-to-peer is built into the protocol at its core. This allows for accelerators to move data through the fabric without that data passing through the host core's coherency domain, creating a lower latency total solution. So Hiren, maybe you can talk about some of the proof of concepts that the Gen Z consortium has been working on and showing off over the last few years in this space.
Well, thanks, Erich. Yeah, so I'm going to take us back in time a bit, go over what the consortium has shown over recent years at Supercompute and the FMS conferences. At these conferences, we've had a large group of Gen Z member companies come together and show proof of concept demos. We've had x86 servers from HP and Dell and non-x86 architectures from IBM mixed inside a single rack, sharing 3 media boxes and 2 levels of Gen Z switches. As Erich mentioned, the initial what we call host fabric adapter, or HFAs, connecting all of these servers were indeed NVMe based. They have evolved since then to be basically PCIe based, and then we also did a demo with a UPI version as well. So again, we've had a mix of processors from AMD, Intel, IBM. We've had Gen Z memory modules, or ZMMs, that were provided from Smart Modular. We had cables from guys at Samtec and others as well. Other contributors to the proof of concepts included Samsung and SK Hynix, both of whom had accelerators in the box connected via Gen Z. So the full rack that we've shown in the last few conferences is shown in the upper right. And the media box, which contains up to 6 ZMMs, is shown in the bottom right. As with the guiding principle number 1, don't break legacy software. So our HFAs have sort of hidden Gen Z behind NVMe or PCIe in both of these cases. So we were able to demo off-the-shelf and unmodified in-memory databases. We ran, I think, SQLite software on these, running multiple host nodes out of the pooled memory environment. So again, this is all stuff we've done and shown in the last few conferences. Let's talk a little bit about the hardware that supports these proof of concept designs. Most of the hardware used in the proof of concepts to date have been off-the-shelf boards that are available from folks like Molex, Bitware, and Alpha Data. The Bitware boards shown on the top left and the bottom right have been used for our PCIe, NVMe, or the ARM bridges to Gen Z. The Alpha Data board, shown in the bottom left, was used as a 12-port Gen Z switch. The Gen Z memory module, again, or ZMM as we call it, was built by Smart Modular Technologies and is shown in the top right. While there's more detail on this ZMM in other webinars from the Gen Z Consortium, the main takeaway here is the ZMM is a DRAM fabric-attached memory module supporting integrated switch functionality, and it's implemented as a Gen Z responder component. Capacities for that ZMM range from 64 gigabytes to up to 256 gigabytes. So this slide provides details on the media box hardware. The media box hardware supports from anywhere from 1 to 6 ZMMs. Using the largest ZMM sizes, the media box can support up to 1.5 terabytes of DRAM. Again, this is with fully populated 6 ZMMs in there. The media box shows in this picture the Alpha Data board, which is used as the switch. The switch has 4 external 100 gigabit per second QSFP cages for multiple connections to servers. Using a Samtec FQSFP expansion card, it is possible to replace the ZMM slots with additional ports to get a full 12-port switch. So what you could do is convert the media box into a switch box, basically. The diagram on the right is an example topology that shows 3 servers communicating to all of the ZMMs inside the 2 media boxes. These servers can access the ZMMs in either 1 switch hop or 2 hops. Additionally, we've included the ARM UDK ARM Orthos board in there as well. So in addition to the media box, which is available today, micro development kit is also available, and that was introduced last year. The micro development kit, or UDK, consists of an ARM-based Gen Z host bridge called Orthos and up to 3 ZMMs. The kit is currently used by the Gen Z Linux Subsystem Software Development Group for software development. Because the UDK can support 2 Orthos boards, a variety of topologies are possible. A single Orthos board can be used for memory expansion testing. A dual Orthos setup with 2 Orthos boards and 3 ZMMs can show memory sharing or pooling. Finally, combining the UDK, the 2 Orthos boards, with the Gen Z media box, which I showed in the earlier slide, allows for even more elaborate topologies. I want to emphasize how small, or micro, some may call it, this kit is. You can see a picture of the kit next to a typical laptop. This should give you some perspective on the size of the kit. So while the kit was designed for software development, it does provide a lot of flexibility, and it's heterogeneous by nature. So recall earlier that I did mention that the ZMMs have built-in 4-port switches. Each ZMM can be connected or is connected to each other using a backplane that's shown in the middle. Therefore, when using two Orthos cards, one can make a mini fabric using the backplane and the built-in switches on the ZMMs. The final diagram shows how all the ZMMs and the Orthos bridges are connected together in the fabric. I mentioned that this kit is a good starting point for software development and is currently being used by the Gen Z Linux subsystem group. Erich, can you elaborate on that?
Yeah, sure, Hiren. So as Hiren mentioned, the micro development kits have been out for a little while, and we have a good group of companies that have been playing around with these kits and working on Gen Z software. So using the small, low-cost development kit, we've been able to work on a Gen Z Linux subsystem, bridge drivers, and a prototype fabric management software called Zephyr, along with a local management service named Llamas. The subsystem and fabric management software are open source and available on GitHub if you want to take a look. I'll put a link to the GitHub site in this slide. The diagram on the right shows Zephyr and Llamas running on a manager node, and Llamas is running on the managed node to the left. The northbound interface on the manager node also has additional interfaces to future composability and resource managers, along with concept fabric manager GUI. The goal here is to be able to leverage some of the Open Fabrics Alliance work that will connect to Zephyr using Redfish over Ethernet to communicate fabric model information and configuration requests between these various management entities. If you want a fast but deeper dive into this fabric management work and a live demo, please check out the recent presentation from Jim Hull at the OFA workshop, which is available on the Gen Z Consortium YouTube channel. We also put a link to that in this slide here. In this talk, Jim walks through a fast and furious overview of Gen Z management infrastructure and does a live demo of the Orthos Gen Z ARM host and simple fabric configuration processes. So what we've learned. So we've done a lot of proof of concepts. We learned a lot of things. So some of them are, FPGAs are wonderful prototyping tools, but they're expensive and power hungry and not particularly low latency. We had to add in lots of pipeline stages to be able to close timing of the design, and the transceivers are designed to work with every protocol under the sun, which is great from the flexibility perspective, but not exactly low latency. As such, the load to use latency across from an FPGA-based host bridge through one or more FPGA-based switches to a media controller, which is implemented in FPGA, does not exactly show a representative latency of what could be achieved if these devices were implemented in ASIC. But they're great for prototyping and showing functionality. It's a bit of a challenge to do apples to apples comparison between FPGA implementations and ASIC implementations of different protocols. I will say though that the 12-port switches that Hiren talked about in the media box do have relatively low latency even in FPGA implementation. This is primarily due to the very efficient packet relay architecture that Gen Z switch offers. Load store latency is critically important if you're trying to run legacy software to FAM. Bandwidth and latency are still much better than local NVMe. We've run a few comparison tests between those technologies at various demo venues. Large in-memory databases, which result in high CPU cache misses, slow down as compared to local memory. It's not really any surprise, however, because accessing remote memory, particularly through one or more switch hops, will always be inherently longer latency than local memory. So moving acceleration functions into the devices can improve total operational latency. So we can start to leverage some of the computational storage techniques in fabric-attached memory to make computational fabric-attached memory. So where we're going, so keep all the load store goodness, allow legacy software to run without modification, enable standard kernel-owned memory, and present a distinct NUMA domain to the OS describing latency characteristics. Leverage existing infrastructure where possible. For shared memory, try to leverage network file system know-how for synchronization between multiple nodes when it makes sense to do so. But try to do it in such a way that still supports direct access to the media in a byte addressable manner. When performing larger data movements than cache line adds and evics, try to make intelligent use of DMA. Additionally, a specialized DMA or dedicated hardware to support remote atomics originating from user space. Put accelerator processing elements, or PE, into the media controllers and try to minimize data movement where possible. This can reduce operational latency and minimize energy for a particular operation. Try to keep this process as simple as possible, but as powerful as we can. So this reminds me of an old quote from many decades ago from Seymour Cray. If you were plowing a field, would you rather use which would you rather use? 2 strong oxen or 1024 chickens? So this is a good one, as it reminds us of what can be done with powerful CPUs, but hints at another way to think of the problem. What if you're looking for grubs in a field as opposed to plowing the field? What would you prefer then? In the next few slides, I'll show an example block diagram for a Gen Z host bridge, how the address mappings from the host to the fabric-attached memory can add some complexities, but also opportunities. Okay, so here we have a bridge component block diagram. On the left-hand side, we have local memory. This is connected to the CPU in the middle via a DDR bus and is addressed using physical addresses. The CPU block has MMU and IOMMU and a whole bunch of cores. Attached to the CPU, we've got a Gen Z bridge on the right. This connection could be made via standard PCIe bus, which is suboptimal from a caching perspective, or CXL, or could be integrated into the SoC using an internal bus such as AXI. So in the bridge block, you see a requester ZMMU, which performs the host physical address to Gen Z address translation. A physical address goes in and a Gen Z address comes out, including all the Gen Z packet goodness like component IDs and region keys and all of that. This feeds into a requester, which takes care of end-to-end packet retry, among other things, and feeds into a switch where various mapping structures control which egress interface the request packet goes out on. On the flip side, to the requester ZMMU is a responder ZMMU. This isn't explicitly required on a host bridge, but like many things in Gen Z, it's optional. It does allow for interesting functionality for shared memory and messaging coming in the opposite direction from the requester ZMMU. In the middle, you see a DMA and some control space structures, which are used for component configuration, control, error reporting, and handling. Main takeaway of this drawing is the CPU core sees into the requester ZMMU with a very large physical address, up to 64 bits in Gen Z, which will likely be configured with many Gen Z components mapped into a flat and contiguous address to the host. So here we kind of zoom in on that requester ZMMU and ignore some of the right-hand side of the previous diagram. So as mentioned before, the host sees a nice flattened address range due to the Gen Z requester ZMMU. The requester ZMMU has 2 supported modes. One's a page grid, one is a page table. Page grid is simpler hardware and lower latency solution compared to the page table-based ZMMU. And this is what I'm showing in this simple diagram. The page grid ZMMU is made up of two main table structures, page grid table and the page table entry table, or PTE table. For simplicity, I show only a single page grid page table, but fundamentally, a page grid-based ZMMU can have multiple page grids, each communicating a variety of page sizes and point into the PTE table at particular offsets, which is fully configurable. This allows for the flexibility of supporting multiple page sizes and addressing a very large amount of memory through a relatively small silicon footprint structure. Another bit of complexity that I'm ignoring here in this diagram is the requester interleave potential. But you can simply consider that to further improve performance by spreading data and even finer resolution across multiple memory components. The right-hand side, I'm showing 4 separate Gen Z modules, or ZMMs, each with a processing element, or PE, capable of doing some accelerator function such as searching or sorting or atomic operations like fetch and swap, compare and swap, decrement, add, decrement, for example. The color scheme in this diagram is attempting to represent that various pages in host memory may be spread across multiple ZMM in a configurable manner. Main point that I'm trying to get to in this slide is showing one level of difficulty when trying to implement computational fabric attached memory, or CFAM. Each ZMM component doesn't see the full picture, it only sees a part of the data set. This is not bad if the data set is structured in such a way that portions of the database are spread across the ZMM in a manner that the PE within the ZMM can see enough of the data to be useful, but it is an added level of complexity. Since the CFAM can see only a relatively small aperture into the data set, the distribution of processing elements within the CFAM still does allow for scaling of performance, even with relatively low-powered CPUs or processing elements within the FAM. It's easy to think of use cases here where a search operation is armed across hundreds or thousands of ZMM, where that search can be performed in parallel, and simply the result can be returned instead of having the host CPU worried about reading all the data into its local cache and doing the search manually. Accelerator functions within the host bridge can see the whole data set, but suffer from a similar load latency from the host CPU, although some custom acceleration hardware can make up for that latency. So with some intelligent software, CFAM or other fabric-attached accelerators can offload computational effort from the CPU, lowering CPU load or allowing the CPU to focus on performing more general-purpose tasks. This can also reduce host bus and host DDR bandwidth, further improving general CPU performance. Additionally, and this one's not thought about very often first order, but this can help spread thermal load, enabling lower cost and more dense servers to be deployed, and purpose-built media storage and accelerator appliances to be architected, which is a new and interesting system design approach. And if done right, it can improve total system performance. So I say bring on the chickens. So bringing it all together, bridges which connect to low latency cacheable hosts interfaces, accelerator devices in bridges and switches and standalone accelerators, and computational or computational fabric attached memory. Software to compose and orchestrate the fabric components, and purpose-built software to take advantage of the accelerator functions, ideally via library changes. So back to you, Hiren.
Thanks, Eric. I certainly hope somebody counted all those chickens. There should be 1024 of them. Anyway, sorry about that. But hopefully everyone has had a chance to understand the challenges related to heterogeneous computing and how Gen Z can help. We've also discussed in this webinar using Gen Z fabrics while still keeping the guiding principles for heterogeneous computing. We've also talked about what is next in terms of fabric-attached accelerators. So I want to thank you for your time, and I think we have a time for at least a few questions. So, Rachel?
Yes, great. We have a few questions. I've gotten one question that may be related to another, so I'm going to sort of combine those. I'm hoping you guys can help. So one states, basically, I understand that getting a hold of some of the cards is difficult. Would it make sense to have these pulled together into a single item that can be ordered? And combined with that sort of question is, how do I order one of the media box development kits or micro development kits? So I guess looking at, how do people source these items?
Yeah, Eric, I can take that one, and if you want to add to it. But let me start. I think, first of all, I think our industry is suffering a little bit from long latencies and silicon shortages, but I think that is adding to the difficulty in getting hold of some of these cards. But I think what my answer there would be, it is worth exploring to see if things can get pulled together. I'm wondering if the question is talking more about like pulling together with multiple companies, like grouping orders together. If that's possible, I mean, I think Intelliprop could try to help. Maybe the consortium could try to help with things like that. But as far as how to order the kits and stuff, I think there's a slide coming up that has some information on websites and links and contact information on who to go to get some of these things. Rachel? Eric, anything you want to add to that? Sorry.
Yeah, just one piece of clarification. We're talking about heterogeneous compute, and you said industry suffering from long latencies, and I agree with that, but I think you meant long lead times.
Long lead time, sorry.
Yeah. Anyways, yeah, so I think there's value in exploring doing sort of more bulk orders and trying to get these things put together. There are some support issues or RMA issues that would need to be worked out on that side of things, but I do think there's probably some value in taking a look at that.
Great, thank you. The next question was, is the Linux work for fabric management that you mentioned in the presentation open source? And if so, where can I find it?
Yeah, so the goal for all of that work is eventually to upstream it to kernel.org. But right now, all that work is open source and is up on GitHub. So I think we've got a link to where that can be found in one of the earlier slides. But it's, yeah, if you just do a Google search for Gen Z Linux, it's one of the first results that show up. And I don't know if my email is anywhere in this slide deck, but you can certainly email me and I can add you to a list to start attending our pretty much every Thursday meeting for Gen Z Linux subsystem development, where we go over progress on software development. We talk about different enhancements to some of these proof of concept hardware designs in the host bridges and switches and ZMMs and such. We talk about things that we want to enable and improvements that can be made. It's a pretty good group of folks working together on that. So if you can shoot me an email, I can add you to that distribution.
Another option there would be to go to the Gen Z website, genzconsortium.org, and through the contact us page, you can request that we make a connection with Erich for you. Another question, it looks like our final question right now, is more of a partner question, a partner organization question. So how do you see CXL and Gen Z working together for heterogeneous computing?
Hiren, do you want to take that, or do you want me to?
Go ahead. Go ahead.
Sure. Okay. So I think we talked about this a little bit earlier, but we've been doing these POCs with different host bus attachments, PCIe and UPI were two of them. I think CXL enables a very nice host connection point, which is cacheable and low latency. That will really enable some of the connection into Gen Z Fabric, which will enable more scale than what CXL's currently targeting. So I think there's some pretty great collaboration that can be made with CXL as a host connect and Gen Z as the fabric interface. So I really see CXL unlocking Gen Z's potential for heterogeneous compute, and I'm really excited to see what the industry starts to work on with those two specifications and protocols working together collaboratively.
Great. I think that's all of the questions for today.
Well, thanks, Rachel. Those are definitely some great questions, everybody. Before we go, I did want to share this slide that does talk about the information we covered today, how to get your hands on a development kit, bit streams, or even support the fabric management work. So this slide should help you get in touch with the right folks for those various objects. So I want to end the call. I want to end with a call to action. If this is of interest to you, please join the Gen Z Consortium and contribute. And thank you for your time.
Great. Thanks, everyone, for attending today's presentation. And thank you, Hiren and Erich. If you have any questions, again, please do visit our website at genzconsortium.org. And you can follow us on Twitter and LinkedIn at Gen Z Consortium to get regular updates and learn more. We also have a coffee chat taking place May 4th. If you visit the website, you can register for that. And we would love to have folks join that and ask any questions related to Gen Z technology, industry interest, and that type of thing. So hope you can join us for that as well, and be on the lookout for our next webinar. Thanks again, and we hope to talk with you soon.